Venom has a way of hijacking your imagination before you even understand what it really is. The word alone pulls something ancient out of the human brain. A flash of fangs. A sudden strike. A pain that feels deliberate. But venom isn't evil, and it isn't random. It's one of nature's most refined tools, engineered over hundreds of millions of years to solve a single problem as efficiently as possible. How do you stop another living thing in its tracks before it hurts you, escapes you, or eats you first? That question gave rise to some of the most sophisticated biochemical weapons on Earth. And today, we're putting two legendary venom users side by side. One is feared for its speed and raw stopping power. The other is infamous for its subtlety and precision. Snake venom versus spider venom. If these two systems were measured head-to-head, which one really wins? Before anything else, one misconception has to be stripped away. Venom is not poison. Poison harms when it's swallowed, touched, or inhaled. Venom only works when it's injected. That single difference changes everything. Venom has no room for error. It has to enter tissue directly, spread fast, and overwhelm the body before the victim can fight back or flee. That pressure shaped two wildly different strategies in snakes and spiders, even though both rely on venom to survive. Snakes are built for confrontation. Not because they want it, but because they can't afford a prolonged struggle. A snake that grapples with prey risks broken fangs, damaged jaws, or fatal injuries. Venom solves that problem. The moment a snake strikes, the clock starts ticking. Many venomous snakes don't even hang on. They hit, release, and retreat. The venom does the rest. That's why snake venom is designed for speed and scale. It has to work on animals that may be nearly as large as the snake itself, sometimes larger. Rodents, birds, reptiles, and mammals all fall within their evolutionary target range. The delivery system reflects that urgency. Venomous snakes use hollow or grooved fangs connected directly to venom glands. In vipers, those fangs fold back like switchblades, snapping forward during a strike and plunging deep into flesh. In cobras and other elapids, the fangs are shorter and fixed, but the venom is no less lethal. Either way, the result is the same. A high-pressure injection that pushes venom deep into muscle and bloodstream within milliseconds. What's inside that venom is where things get truly terrifying. Snake venom is not one toxin. It's a chemical orchestra. Neurotoxins interfere with nerve signals, shutting down communication between the brain and muscles. Hemotoxins attack blood cells and clotting mechanisms, turning the circulatory system against itself. Cytotoxins destroy tissue at the bite site, causing swelling, necrosis, and extreme pain. Myotoxins break down muscle fibers, releasing toxins into the bloodstream as the muscle dissolves. Some venoms focus heavily on one system. Others attack several at once. That redundancy is intentional. If one pathway fails, another will finish the job. This is why snake venom is such a serious threat to humans. Our physiology isn't that different from the animals snakes evolved to hunt. Our blood, nerves, muscles, and organs respond to those toxins in very similar ways. In many cases, the venom doesn't even need to kill directly. It just needs to immobilize long enough for shock, organ failure, or secondary complications to take over. Spiders live in a completely different world. They are not built to overpower prey with force. They are fragile, lightweight, and vulnerable. Their strength lies in timing, positioning, and efficiency. A spider doesn't chase. It waits. It traps. It strikes only when the odds are overwhelmingly in its favor. Venom, for spiders, isn't about dominance. It's about control. Instead of long hollow fangs, spiders use chelicerae, sharp, fang-like mouthparts that puncture and grip. The injection is far less dramatic than a snake's strike. The dose is tiny, measured in micrograms. Spiders can't afford to waste venom. Producing it costs energy, and energy is survival. Many spiders even perform dry bites when threatened, injecting little or no venom at all. It's a warning, not an execution. Spider venom is also built with a very different target in mind. Insects and other arthropods. Creatures with compact nervous systems, rigid exoskeletons, and entirely different biology than mammals. Spider venom is often exquisitely specialized. Some toxins bind to very specific ion channels in insect nerves. Others shut down muscle contraction or cause immediate paralysis. Many venoms include enzymes that begin breaking down tissue from the inside, effectively liquefying the prey so the spider can drink it later. For an insect, it's a death sentence delivered with surgical precision. For humans, that specialization is usually a blessing. Our bodies are larger, more complex, and less sensitive to many of the molecular targets spider venom evolved to exploit. In most cases, a spider bite results in localized pain, redness, swelling, or itching. Uncomfortable, but rarely dangerous. Millions of people are bitten by spiders every year and never require medical treatment. That doesn't mean spiders are harmless. Nature always keeps a few wild cards. Black widow spiders produce a neurotoxic venom that causes intense muscle pain, cramps, sweating, and nausea. Brazilian wandering spiders possess venom that affects nerve signaling and blood flow, sometimes causing severe systemic symptoms. Funnel web spiders produce venom that can overwhelm the nervous system if left untreated. But even in these cases, fatalities are extremely rare in the modern world. Antivenom and rapid medical care have turned what was once deadly into something survivable. One fascinating parallel between snakes and spiders is restraint. Despite their reputations, both animals often choose not to use venom unless absolutely necessary. Snakes deliver dry bites surprisingly often. Venom is precious. A snake that wastes venom may struggle to hunt later. Spiders make similar calculations. A bite doesn't automatically mean venom injection. Threat displays, bluff strikes, and escapes are preferred whenever possible. This reveals something important about venom that fear often hides. Venom is defensive as much as it is offensive. Neither snakes nor spiders are out hunting humans. Most bites occur when the animal is startled, cornered, or accidentally stepped on. Venom exists to end encounters quickly, not to seek him out. From a biochemical perspective, snake venom tends to be broad and aggressive. It hits multiple systems at once, creating cascading failures throughout the body. Spider venom is often narrow and elegant, targeting specific pathways with minimal collateral damage. One overwhelms. The other disables. These differences have made both types of venom incredibly valuable to science. Researchers study snake venom to develop blood-thinning drugs, treatments for high blood pressure, and therapies for clotting disorders. Spider venom has shown promise in pain management, neurological research, and even the development of environmentally friendly insecticides. What once inspired terror is now saving lives in laboratories and hospitals around the world. So which venom wins in a real fight? If the measure is danger to humans, snake venom wins without question. Its speed, volume, and broad biological impact make it one of the most medically significant natural toxins on Earth. If the measure is precision and efficiency, spider venom takes the crown. It does exactly what it needs to do with minimal waste and astonishing specificity. But the real answer isn't about victory. It's about strategy. Two creatures faced the same evolutionary challenge and solved it in completely different ways. One became a biochemical sledgehammer. The other became a molecular scalpel. Power versus finesse. Speed versus control. Both are masterpieces shaped by time, pressure, and survival. Venom isn't evil. It isn't cruel. It's clever. It's efficient. And it's a reminder that some of the most powerful forces on Earth come not from size or strength, but from invisible chemistry working with terrifying precision. Thank you for watching. If you have ideas for what we should explore next, drop them in the comments and we'll be sure to credit you. Don't forget to like, subscribe, and stay curious about the hidden systems shaping the world around you.